Now we're going to look at compositions of functions and inverse functions. So you've really been doing compositions of functions before when we were looking at that difference quotient, the f of plugging in x plus h wherever you saw an x minus f of x all over h. That was kind of like you were dealing with a composition of function. Maybe g of x was x plus h, and you plugged that in wherever you saw an x in f of x. But let's just go over it a little bit and let's talk about the terminology and the notation. So my objective is after this lesson, you'll be able to form the composition of two functions. You'll be able to determine if a function is one-to-one by using the horizontal line test. Show that two functions are inverses of each other by verifying that f of g of x equals g of f of x, which is equal to x. You'll be able to find the inverse of a one-to-one function, and you'll be able to graph inverses of functions. And those are by reflecting the graph of the functions across the line y equals x. Okay, so composition of two functions, where you're plugging one function in wherever you see an x of another function. So definition for two functions f and g, the composite function, denoted by f with a little circle in between, and then g. It's defined as, so this f little circle g, f of g of x, f parentheses, g parentheses, x, and your parentheses. So that's the notation for the composite functions f of g. And then if we're looking at the domain of f of g consists of all those values x in the domain of our inner function, g. And then remember, if we plug in values for x and for g of x, then our y value is going to be plugged in that output and wherever you see an x and f. So we have to be worried about the output of g of x. And that needs to be in the domain of f. Okay, so let's look at some examples. So suppose that you're given f of x is 1 over x plus 1, and you're given g of x is x squared plus x minus 3. So we want to do the following. We want to first find and simplify the composite function f of g of x. So f of g of x, if it helps you, we can rewrite this as, well, g of x is this x squared plus x minus 3. So we could rewrite this as f of our g of x function, which is x squared plus x minus 3. So we're going to go in here wherever we see an x in our f of x function, we're going to plug in that x squared plus x minus 3. So let's go in to f of x. So we have 1 all over. Let's put parentheses where we see an x, and a pretty big parentheses, plus 1. And so we're going to drop in the input, which is our g of x, x squared plus x minus 3, inside that parentheses. So notice I can simplify this a little bit. This is 1 all over x squared plus x, and then negative 3 plus 1, that's minus 2. So it asks us to find the domain of f of x, find the domain of g of x, and find the domain of f of g of x. Well, if we look at f of x, we do have a trouble spot. So you're looking for trouble spots when you're finding the domain and excluding those values, which give us troubles. So values which we would plug back into the function and we would not get back a real number. It'd be something that was a complex number, imaginary, or it was undefined. We cannot have 0 in the denominator, so we're worried about the value of x that would set the denominator equal to 0. So x plus 1 cannot be 0. So x cannot be negative 1. So our domain for f, this was going to be equal to negative infinity to -1, not including, so parentheses, union -1 to infinity. If we looked at the domain of G, so notice that G of X, which is this X squared plus X minus 3. This doesn't have any trouble spots. It doesn't have any radicals, even powered radicals. It doesn't have any variables in the denominator, and it's not a log function. So we don't have to worry about values. And so our domain of G are all real numbers. So looking at the domain of the composition of the function, well, we would look first at the inner function and exclude anything that our inner function can't have, which it can't have negative, well, all real numbers, it's domain, so we don't have to exclude anything there. We do need to worry about, though, when g of x gives us an output of -1, because we can't plug out in -1 into our f of x function. So we're worried about g of x, x squared plus x minus 3. We don't want it equal to -1. And so let's solve for that and then exclude that from our domain of our f of g of x. And so it's quadratic. I would set it equal to 0. So I have x squared plus x, adding 1 to both sides, -3 plus 1 gives me -2 equals 0. And so looking at that, it looks like it's factorable. There are two numbers that multiply to +2 and add to multiply to -2 and adds to +1. So that would be a +2 and a -1. So x minus 1 all times the quantity x plus 2. So x cannot be 1 and x cannot be -2. Those would be the values that would spit out -1. If we plugged them into g of x, and we can't have that when we plug it into f of x. So the domain of f of g of x, this is equal to, well, negative infinity to -2, not including -2, so parentheses, union -2 to 1, parentheses around of both of those, and then 1 to infinity. So part C, same functions, f of x is equal to 1 all over x plus 1, and g of x is x squared plus x minus 3. This time, though, we want to look at g of f of x. And so we're going to take our f of x function, 1 all over x plus 1, and we're going to plug that in wherever we see an x in g of x. So I'm looking at g of the function 1 over x plus 1. So I'm going into my function of g of x. Wherever I see a x, I'm going to put parentheses for now. So parentheses squared plus parentheses, and then -3. And inside that parentheses, I'm going to write g of f of x, which is 1 over x plus 1. So looking at this, if I'm squaring a fraction, I can square the numerator. So squaring 1 times 1 is 1, all over the square of the denominator. So x plus 1 quantity squared, plus 1 over x plus 1. I'm going to leave a little bit room here because I want to simplify this and I need to get a common denominator. So I'm going to need to multiply by a fancy 1 here to get that common denominator, which I can tell right now is x plus 1 quantity squared. So let's just actually multiply that second grouping, 1 over x plus 1 by x plus 1 over x plus 1 to get the LCD, then bring down the -3. In this case, in order to get a a common denominator, we want x plus 1 quantity squared all over x plus 1 quantity squared. So just getting the least common denominator. For all of those terms or groupings. So we have 1 all over x plus 1 quantity squared plus, well, 1 times this x plus 1 here is just x plus 1 all over x plus 1 quantity squared minus 3 all times, well, let's look at x plus 1 times x plus 1. And that's going to give us, if we distribute this out, that would give us x squared, a 1x plus a 1x, so plus 2x. And then a 1 times 1, so plus 1. So this is right here, x squared plus 2x plus 1, all over our common denominator of x plus 1 quantity squared. So now that we have a common denominator, we can put everything over that common denominator, x plus 1 quantity squared, and we can sum our numerator. So we have 1 plus x plus 1. Let's distribute this -3. Oops, let's go down here and distribute it. Carry the sign with it. So carrying the negative, so -3 times x squared. So that's going to give me a minus 3x squared. A -3 times 2x, so minus 6x. And a -3 times 1, so minus 3. So I'm going to rewrite this descending order of powers for my terms. So I have only one term with an x squared, so rewrite it, -3x squared. Let's combine x minus 6x, which gives us -5x, so minus 5x. And then we have here 1 plus 1 is 2, minus 3, so that would give me -1. So this is our g of f of x. So the next piece wants us to find the domain of our f of g of x. So we already found the domain of f of x. The inner function for f of x, x cannot equal -1. Our domain of g of x we talked about is all real numbers. So we don't have to worry about any output that we get when we plug in any number in the domain of f of x. And so for this domain, only thing we're worried about is x being -1. And so the domain of our g of f of x is -infinity to -1 union -1 to infinity. Okay, so that was a quick review of taking the composition of two functions. So we'll look a little bit more at finding compositions of functions as we look at finding inverses of functions or showing that two functions are inverses of one another. Let's first start with, in order for a function to have an inverse, it has to be a one-to-one function. Well, what is a one-to-one function? So recall, for a function, there is only one y value assigned for each x value in the domain. So graphically, we saw that things were functions before by looking at the vertical line test. So for every, just to recall about functions, to be a function for every x in our domain, that x is only giving us, gives us one output. To be a one-to-one function, it holds a little stronger. So a function is a one-to-one function, and we usually denote this by 1-1. If for each y value, each value of y in the range, there is only one corresponding x value in the domain. So I cannot have two separate x values give me the same y value. If there's two separate x values giving me the same output, same y value in the range, then it's not one-to-one. In mathematics, sometimes we take functions that are not one-to-one and we can create it to be one-to-one. For instance, if you look at a parabola, this is a function because it passes a vertical line test, but there's multiple values of x that are giving me the same y value. And so in this case, this is not one-to-one, but if I took this y equals x squared and I limit my domain, let's say of that as x is greater than or equal to 0 in this case, that would mean that I could get rid of half of this parabola. And then this is now a one-to-one function. So things that are not one-to-one could be made one-to-one by limiting the domain. And when you get into trigonometry, you'll see that sometimes we do that to make our functions one-to-one. So there's a theorem. So just like we were testing to see if a graph was a function by the vertical line test, in this case, to see if it's a one-to-one function, we can see if it passes the horizontal line test. And so this theorem states that a function is one-to-one if no horizontal line intersects the graph of the function more than one point. Okay, so if it's one-to-one, then it's going to have an inverse function. So it says if f is a one-to-one function with ordered pairs in the form xy, then its inverse function, denoted by f, it looks like an exponent of -1, but it really isn't. So f inverse is also one-to-one function with the ordered pairs in the form of yx. So basically all we're doing is we're swapping our x and our y values. Okay, so don't do this. This superscript of -1, the notation f looks like it's raised to the -1, is part of the notation for naming the inverse function. That is not an exponent. And remember, if you had back in algebra, which this is, back in probably a previous course, if you had negative exponents, we can make them positive. If it was in the numerator, we could bring it down to the denominator to make it positive. But this is not the case for f inverse of x. That is not equal to 1 over f of x. And we'll see that as we go through finding our inverse functions. That we're not going to get the same thing as if we took our function and put it underneath 1. So certain things that you should know about graphs and graphs of the inverse functions. So if you have an inverse function, so if f is one-to-one, then we also know that it has an inverse function. If xy is a point on the graph of f of x and it has an inverse function, then yx is a point on the graph of x equals f inverse of y. So that is the domain of f is the range of f inverse. And the range of f is the domain of f inverse. So our domain and our ranges swap for a function and its inverse. Other thing you should know is that the graphs of f and f inverse are reflections of each other across the line y equals x. So if f and g are one-to-one functions, and you plug in g of x wherever you see an x in f of x, so f of g of x, and you took the composition of those two and you get back x for all x in the domain of g, Then when you plug in f of x, wherever you see an x and g of x, so g of f of x, you must also get x for all x in the domain of f. So if you take the composition of two functions and you get back x, and it should happen both directions, then f and g are inverse functions. And we can write that g equals f inverse of x, and we can also write, if we wanted to, f is equal to g inverse of x. So the example in front of us, we're given f of x, we're given g of x, and we want to know, are they inverses of one another? And we want to show why or why not. So we want to show, if we take the composition of these two functions, that we're going to get back x. That would show us that they are inverses of each other. We're given, in this case, f of x is equal to 3 minus 2x, and g of x is equal to 3 minus x. That quantity, 3 minus x, is all over 2. So let's look at f of g of x. So that is taking our g of x function, 3 minus x, all over 2, and plugging it in wherever you see an x in f of x. So let's go through, and f of x, let's put a parentheses where we see an x. So we have 3 minus 2. I see an x, so put parentheses there. And we're going to drop in g of x, which is 3 minus x all over 2. So notice here, I have a 2. This is multiplication in between, so I can simplify. I have a 2 in the numerator, and I have a 2 in the denominator, so those cancel. And so this is equal to 3. You're going to want to take your negative and distribute it to this positive 3 minus x. So I have a negative times 3 is negative 3, and negative 1 times negative x gives me plus x. And so notice that 3 minus 3 is 0, plus x is just x. So it's composition of the two functions gives me x. And so by this theorem, they have to be inverses of one another. Let's show it the other direction. So looking at g and plugging in f of x wherever we see an x and g of x. So we're going to go in and we're going to plug in 3 minus 2x wherever we saw an x and f of x. I'm sorry, an x and g of x. So doing so, we would have 3 minus, I see an x, so put parentheses, all over 2. And inside that parentheses, we're going to drop in 3 minus 2x. So let's distribute that negative sign in the numerator up there. And so we have 3, distributing the negative 1 times 3 is negative 3, and negative 1 times negative 2x, that gives me a plus 2x all over 2. Simplifying in the numerator, 3 minus 3 cancels, so we're left with 2x over 2. And that simplifies to x. So f of x and g of x are inverses of one another. And again, that's because when we took the composition, both directions, we got back x. In general, I'm okay if you show just one way, taking the composition, and you get back x. But depending on your instructor, you might want to show it both ways. Okay, so that we showed that those two were inverse functions of each other. But how do we find the inverse function? And so in order to find the inverse function, first step that you're going to do, you're going to take your function, if it's called f of x, let's rewrite f of x as y. F of x is just another notation of writing y. Once you've rewrite your equation y equals instead of f of x equals, you're going to go in and wherever you see your y, you're going to put an x. And wherever you see x, you're going to put a y. So you're going to interchange y and x. Then in the new equation, we're going to solve for y in terms of x. So we're going to get y by itself, then have y equals. Once we've got y by itself and y equals, we can substitute f inverse of x in for y, and we found our inverse function. So let's look at finding the inverse function. We're given f of x is equal to 4 all over x plus 2. And we want to find the inverse of this one-to-one function. So you guys should be able to graph these. Recall we graphed rational functions. But this is a one-to-one function. X cannot be -2. X equals -2 is a vertical asymptote. But I guess we can look at this. So we have y equals 4 all over x plus 2. So rewrite f of x as y. So now go in and we're going to interchange our x and our y value. So we have x here is equal to 4 all over y plus 2. We want to solve here for y. So let's clear our fraction. We can clear our fraction by multiplying both sides by our denominator, y plus 2. Doing so on that one side, the y plus 2's cancel, which we want. And let's rewrite the left-hand side by distributing our x. So we have here x times y plus 2x is equal to 4. So we're just trying to get that term with y by itself first. And so we could subtract 2x on both sides of our equation. So we get x times y is equal to 4 minus 2x. And now let's get y by itself, and we can do so by dividing both sides by x. And we get y is equal to 4 minus 2x divided by x. And so now we can rewrite y as f inverse of x is 4 minus 2x all over x. So we could go and we could show that the composition of those two functions, either direction, if we plug in one function in for x into the other function and simplify, we should get back x. Let's do one more. So one more example really quickly, because we're running out of time. F of x is equal to 2 square root of x plus 3. And then outside of the radical is -5. So the function is a one-to-one. We want to find its inverse. And then we want to find the domain and range of f and f inverse of x. So right now, let's just find the domain of f of x. And so we have a trouble spot. We have a even powered radical. And so we know what's underneath that radical, x plus 3, has to be greater than or equal to 0. And so I know x has to be greater than or equal to -3. So the domain of my original is the range of my inverse function. So my range of my inverse function is y is greater than or equal to -3. So now let's look at this. You should be able to tell what this graph looks like by transformations of functions. So remember the inside, this is like the parent function, the library of functions, the square root of x, that x plus 3, that's plus 3 is shifting it horizontally to the left 3 units. And this -5 shifts us down 2 units. And this 2 out in front is a vertical stretch. So just kind of reminder of things that we've done in the past. So we're rewriting this as y equals 2 square root of x plus 3 minus 5. Let's rewrite this as x is equal to interchanging our x and y values. 2 times y plus 3 minus 5. We want to solve for y, so let's add 5 to both sides. So we have x plus 5 equals 2 square root of y plus 3. I can divide both sides by 2, but I see I get a fraction. I want to get rid of that square root, so we could just square both sides. So I would get x plus 5 quantity squared is equal to 2 squared. I have to square the 2, which is 4. And squaring the square root leaves us with y plus 3. Let me distribute that 4. So I have x plus 5 quantity squared is equal to 4y plus 12. We want to get y by itself, so let's subtract 12. So we have x plus 5 quantity squared minus 12 is equal to 4y. And then we're going to divide everything through by 4. So we get y, which is also equal to our inverse function, f inverse of x, is equal to x plus 5 quantity squared minus 12, all divided by 4. If we look at this, notice that this actually is a quadratic. And again, we can think of this if we rewrite it. That's 1/4 times x plus 5 quantity squared minus 12 divided by 4 is 3. So from here, you should be able to tell what our vertex is. So it's in that vertex form. Our vertex is -5, -3. Our value of a is greater than 0. So I know our parabola faces upwards. So this point here is 5, -3. So I know that my range of f inverse of x, this is equal to, oh, I should have it right here. Y is greater than or equal to -3. Was there any other stipulation here when I wrote down the problem? Nope. So in here, my range is y is greater than or equal to -3. My domain, it's a quadratic. My domain of my inverse function is all real numbers. And I know that that domain of my inverse function is also the range of my original function. So the range of f of x is all reals. -infinity to infinity. So given a one-to-one function, we were able to find its inverse function, and we were able to find the domain and range of both of those. So a couple other things that you guys are going to need to do is, given the graph, you're going to need to be able to graph the inverse function. Just take points on your graph and swap your x and y values to get new points on your inverse function to graph. I have some videos under the supplemental part for this section that might go into more detail, some more problems. But this is the rest of the finding the inverse of functions for what we're going to do this semester.